At Seco Environmental, we're proud to be your single source for pollution control. It's our mission to protect our shared environment, and we relentlessly pursue that goal by providing reliable products and services to tackle your environmental challenges. Purchasing pollution control equipment can be a complicated process, particularly when you have a system that requires many different pieces of equipment. However, our vast range of technologies and solutions for pollution control and product recovery can eliminate that complexity, lowering your total cost of ownership without sacrificing performance. Across a wide variety of industries, Seco helps ensure you achieve real results. No matter your need, Seco has you covered. Simplify your environmental initiatives with our Seco Environmental family of industrial solutions brands. Seco Environmental is a global leader in air quality and fluid handling, serving the energy, industrial, and other niche markets. Through innovative technology and application expertise, Seco helps you grow your business with safe, clean, and more efficient solutions that help protect our shared environment. We work tirelessly to improve air quality, optimize the energy value chain, and provide custom-engineered solutions for applications including oil and gas, power generation, water and wastewater, battery production, polysilicon fabrication, chemical and petrochemical processing, and more. To learn more, visit secoenviro.com today.
Welcome, and thank you for joining us today for the Seco Certified Continuing Education Series. Today, we will be learning about thermal oxidizer basics presented by Seco Environmental. My name is Mary Rusnak, and I'm the Marketing Manager for the Industrial Air and Fluid Solutions segment of Seco. And with me today is Brian Cannon, our VP of Sales and Marketing for Seco AdWest, and Brendan Boudelier, Oxidizer Applications and Project Engineer. While we wait for everyone to join, I'd like to go over some basic housekeeping items about our webinar platform and also about the PDH certification. First things first, sound issues. So first thing, check your media player, which is on the bottom. Make sure that you're not muted and that it's working properly. There's also a help widget there. Blue arrow will show you a little question mark, and that will help you with any other problems that you may have. And finally, if you continue to have issues, try logging out and logging back in using the link from the email when you registered. Platform itself, at the bottom of your screen are multiple application engagement tools, or as I like to call them, widgets, that you can use. All the widgets are resizable and movable, so feel free to move them around and just, do what you need to do to get the most out of your desktop space. You can expand your slide area to maximize it to full screen or just make it smaller, whatever the case you want to do, just by using the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A widget, which is a little question mark there. To keep ourselves on track, all questions will be held until the end of the presentation, but you can submit your questions at any time. If we don't get to your question live, we will definitely contact you later and get you the answer that you're looking for. A copy of today's slide deck and additional help materials are available in the resource list there on the right. We encourage you to download any resources or links that you may find useful. You'll find all of our links to LinkedIn, Facebook, YouTube, and just for future reference, we do post all of our events on LinkedIn and Facebook, so you can always keep an eye on upcoming events that way. The oxidizer summary that's over on the right-hand side is something that would be very useful for anybody who is taking the quiz later and might need a little bit of maybe help. Professional development hours, or the PDH state information, is also listed over to the right. We are able to offer PDH credits for professional engineers for 36 states right now. If you hover over any of the widgets, it'll basically tell you what they are. So there's a lot of options. You can share via social. You can email me directly from the widgets on the bottom. And then the two more important ones are the check mark, which will take you to secocertified.com. That's where you can sign up for more events, or also take a look at the on-demand archive for the webinars that we've already had this year. And we also have one additional webinar that will be happening on November 18th, and that is industrial ventilation design. So feel free to go over to secocertified.com to sign up for that or for any of our on-demand versions. Now, if you're here for the PDH portion, the two last widgets are probably the ones you're going to want to look for at the end, the test and tracker widget. The test is where you basically take the quiz, and the tracker widget, the one on the very end, is where you check your progress. Once you have filled all the requirements, you will actually get a little box that pops up that you can basically print out your certificate from there. An on-demand version of the webcast will be available after the event and can be accessed using the same audience link that was sent to you earlier, and all of the interactivity remains, including testing capabilities. So if you get accidentally booted off, don't worry about it. You can come back on and print everything out, or you can come back later and take the test if you run out of time and can't do it today. So quick overview of the PDH portion. Today's webinar is worth 1 professional development hour. You need to be here for at least 50 minutes. This is both for the live and on-demand version. As I mentioned, if you get interrupted, you can just log back in and continue. You must complete and pass the test, which is basically getting 8 out of 10 right. Once you fulfill all those requirements, you'll be able to print your certificate out of that certification widget. Suggest that you guys keep a log of this. SECO will keep records for 6 years. If you have any questions related to any of this, feel free to just email me directly. That's my email. And let's take a look here. And just again, and also the webinar is 1 hour long, but just so everybody's aware, we will keep the platform open for an additional 30 minutes afterwards so that you can finish up your test, print out anything that you want. So in terms of the outline, these are the things that we are going to cover here today. Definition and overview. We're going to look at the 3 T's. What does that mean? Some oxidizer components. What are the different types that you would use and where? Basically some design and process considerations, and then a little bit of examples at the end to get you an idea of how these are used. And we're going to start today's webinar with a poll question. And if you've attended our events in the past, you'll know that you will be able to answer the poll in the next slide. So starting off here with a little bit of our Halloween themed poll question. How much experience do you have with thermal oxidizers and VOC controls? And there's your options there. You're an expert. I have some experience. I have a little bit of experience in what in the world is an oxidizer. So I'm going to advance the screen here, and this is where you can put your answers. Okay, I'll give you a second here just to finish up your answers, and we'll take a look at the results. Okay, that's a nice variety of experience that we have there. It looks like the majority at this point have a little bit of experience. Some are really new into the experience itself and what an oxidizer is, and then we have a couple experts in there. I think this is going to be a great presentation for all of you, even if you're an expert. There's a lot of information in here, as well as some things that'll definitely help guide you in terms of selection and the process and any future needs that you have. So I'm going to turn this over to Brian Cannon, who's going to actually start the real presentation itself with all the info. Brian?
Many thanks, Mary. Hopefully everybody can hear me well. I'll say a good morning, a good afternoon, and a good evening to all our attendees here for the webinar. We have attendees, I believe, from all over the world and probably just about all the time zones. So we certainly appreciate your time. I hope this webinar, we find everybody safe and healthy as well in these trying times of the pandemic. So today we're going to be covering a wide range of thermal oxidizer basics. We're going to be probably hitting the tops of a lot of waves and outlining a lot of the various thermal oxidizer and sometimes they were called many years ago fume incinerator technologies and solutions that are available. And if you look at this, what really demands or what is the driver for why anyone would want to use a thermal oxidizer? And this slide here is really sort of a timeline, at least here in the United States. We've been fairly progressive through the decades on air pollution control as well as on VOC abatement. And a lot of our federal legislation didn't start until the 50s here in the United States. So a lot of this is just fairly recent in the last 50 to 70 years, these stringent guidelines, and they've spread throughout the globe. I first started in thermal oxidizers back in fume incinerators, is when they were called, back in 1977. We've gotten sophisticated in the 80s with calling them thermal oxidizers, and then we saw a lot of the RTOs really take over a lot of the recuperative and afterburner applications. But the drivers here are the various legislation acts, at least here in the States. I know there's a lot of countries that have emulated the U.S. EPA, the federal EPA Clean Air Amendments, Titles 1 through 5. And obviously on Title 5, that allows the various state EPAs here in the U.S. to develop and enforce detailed industrial air permit programs and work with the various industries, plants, and so forth. But they've gradually gotten more stringent through the years. There's been different amendments that have been specifically for various industries. For example, there's MACT standards, M-A-C-T standards, for the wood industry, for the composites industry, paint finishing, and so forth. So we could go on with this, and there could be all kinds of training on these MACT standards and how to meet them, and on Title V. We're going to have to save that, I think, Mary, for some later webinars. The VOC, we'll go through just a couple real quick definitions here. The volatile organic compounds, or VOCs, as we refer to them, typically there are a lot of solvent fumes and vapor phase gases. They contain carbon. They can have acids in them. And a lot of these will have aldehyde type components, the longer chain hydrocarbons, and they cause noxious and toxic type fumes and smelly odors. And typically these need to be broken down or abated or oxidized or incinerated at typically, it's around 14 to 1500 degrees Fahrenheit and greater on thermal oxidizer technologies. We'll talk a little bit about catalytic oxidizers. Brendan and I will do that here shortly, and that's at a lower temperature, similar to your catalytic converters in your cars. But the VOCs are generally non-water soluble. Wet scrubbers are generally not a good application for these. So if you have VOCs, you're probably pretty well looking at thermal oxidizers, maybe a catalyst option. You could be looking at carbon systems, and you could also be looking certainly at biofilters, and we'll just touch on that option as well to give you an overview. Also, the hazardous air pollutants, or HAPs, the national NESHAP on stationary sources, obviously there's hazardous air pollutants, and those have to be dealt with as well. They can cause cancer and carcinogenics and everything from skin rashes to nervous system damage and so forth. So generally they can be wet scrubbed. There's very few, and some of those can be handled with a combination of both oxidizers and a scrubber on the tail end. And we'll talk about those a little bit later. So if you hear the word HAP, that's hazardous air pollutants. The NESHAP is the National Emission Standards for Hazardous Air Pollutants. Probably the biggest definition, and it's been time honored through the years as tried and true, are the 3 T's. Sort of the basics of thermal oxidation or thermal incineration technologies and how to break down these hydrocarbons, whether they be a longer chain hydrocarbon with lots of aldehydes, or if it's a smaller type compound. But as I mentioned, oxidation temperatures typically are 1300 degrees and greater. Most compounds you're going to see 1500 degrees, sometimes 1600 degrees Fahrenheit. A lot of oxidation systems will actually require greater than that, sometimes 1800 to 2000 degrees if you get into PCBs and things like that. The ability of a catalyst unit, those typically will light off or activate at 550 degrees Fahrenheit to about 800 degrees Fahrenheit. So catalyst is not applicable for all applications and all VOCs. You typically want to stay away from heavy metals, from silicone-laden compounds, from acids, heavy metals like lead, antimony, and those types of things. But catalysts can provide some energy efficiency because they use a lower temperature to activate on the catalyst. And the purification reaction there is not in a retention chamber, but over the catalyst. We'll talk about that later. The time element, VOCs can spend typically a half second up to 2 seconds or more retention time or residence time at these higher temperatures to ensure complete oxidation. You basically bake the VOCs at a certain temperature. And you also do need turbulence in the combustion chambers while you're doing the temperature. And the turbulence comes from adequate mixing for the oxygen. You want to have oxygen with the VOCs. Typically, you can have burners through on recuperative units or DFTOs through the burners. There's mixing plates in a lot of cases. With an RTO, or regenerative thermal oxidizer, you get mixing in the various media types. Could be turbulent flow through, say, saddle media, or laminar flow through block type medias. And we'll touch on that here a little bit later. But typically, you're going to need about 15 to 16 mole percent O2 for proper combustion, with the various burners available and stoichiometric ratios and so forth. So the 3 T's all work together, and we'll be talking about that throughout our presentation. When to use a thermal oxidizer. Obviously, you may have a Title V permit if you're here in the United States. Obviously, this is all VOC driven with the regulations from your various national EPAs or Ministry of Environments or Department of Environmental Protections or the various states or even local. Here in the States, the South Coast Air Quality Management District, that almost takes precedent over everything in the state in the lower part of California. And you have the Bay Area up top as well. And they work with the California Air Resources Board and US EPA. So basically know what you're under as far as regulation with the regulators. The regulators are your friends. They're trying to accomplish compliance, and they want you to do it in a cost-effective manner. If you have odors or reactive gases, you're going to need a thermal oxidizer at higher temperatures there. A lot of times you'll see roaster fumes from coffee roasters and things like that have applied thermal oxidizers through the years, actually afterburners, to take care of the fumes and smoke. But there's a lot of odoriferous compounds you'll see in food processing, rendering, fragrance, and perfume type manufacturing applications. There are VOCs and solvents in there, and there are some longer chain hydrocarbons on that. The requirement for the high VOC destruction is typically done percentage by weight or volume. And the higher VOC destruction efficiencies in most cases eliminate on a practical basis the use of biofilters across the board or carbon filters. Carbon filters have to be replaced and rejuvenated. Thermal oxidizers typically provide 95 to 99% plus VOC DREs. You're looking typically on biofilters and carbons 80 to 90% on the VOC DRE. They can get higher than that, but you're going to need more surface area, larger carbon beds or canisters, larger biofilters. Some of these things can get as big as almost a football field. So you're going to need more surface area, more residence time inside the biofilter. Another thing to consider, if it looks like we have many experts and probably people that have older oxidizers at their plants here attending, Mary, but a lot of the older DFTOs, the direct fired afterburners and recuperative units, they typically use a lot more energy than RTOs. And RTOs can be retrofitted on them to achieve higher destruction VOC or equal high VOC destruction. And they can also reduce these NOx emissions and also the energy usage, which is key because energy costs are only going to go up in the future. There's many choices of thermal oxidizers. As I mentioned, we have the direct fired, also called afterburners. You can get these in a horizontal or vertical fired type arrangement. There's the recuperative thermal oxidizer that would typically use a shell and tube or plate and frame type heat exchanger to recuperate and reduce energy. Typically, those are about 35 to 80% thermal efficiencies. The RTO thermal oxidizers, those are between 90 to 97% thermal efficiency. We see that as being one of the more flexible technologies. You can also have an RTCO option, where you can have the RTO operating with a catalyst bed at the top at lower temperatures, and we see that a lot in the wood industry. There's flameless versus burner-fired RTO options. Most of these systems can be done. We've seen and have done RTOs ourselves in both electric heat and burner. And there's also catalytic units out there that operate electrically and also have burners. And typically, a lot of industries will call these fume incinerators. If you have especially high VOC concentration flow rates. Concentrators are used there for high flow rates and low volumetric inlet loadings. And usually we'll put a small DFTO or small oxidizer or some type there. Typically you're going to see that in the paint industry, in composites, in several of those types of industries. We have the zeolite rotor module concentrators. We're just going to touch on these today. We could probably do a webinar on these as well, Mary. Typically, the concentrator media of choice is a zeolite rotor module, hydrophobic zeolite, and it's typically a honeycomb structured adsorbent. It absorbs the VOCs and then it's desorbed. You'll typically see 10-to-1 and greater VOC concentration ratios. So say if you had a 100,000 CFM paint line, you could put a concentrator, and typically if you were at 10-to-1 concentration ratio, you'd have about a 10,000 SCFM smaller oxidizer on the tail end. So your capital cost lowers and your energy costs are significantly lowered through that 10,000 SCFM oxidizer as opposed to having a large 100,000 CFM RTO. And of course, you typically see those in the paint industry, semiconductor fab, composites, and just general spray coating. Low inlet temperatures, they don't like acids. The concentrators can be very finicky, so they're not applied to all applications. Thermal oxidizer types, the three major types that we see besides the direct fired are typically the RTO. That's been the most flexible through the last probably 2 decades, 3 decades. The regenerative thermal oxidizer regenerates various beds, typically 2 to 9 or 11 beds, depending on the design. And you can get between 85 and 97% primary heat recovery. And you get good mixing through the ceramic media. And there's a couple of pictures there in the middle showing some ceramic media, some block medias. They typically look like catalytic converters in your car. And you can see some ceramic saddles on the lower left. The recuperative oxidizers use a shell and tube or plate and frame heat exchanger. The upper left shows a shell and tube. I think those are 1.5 inch round stainless steel tubes. Those have expansion joints with the various bundles to prevent leakage, to get you the high destruction efficiency. You will get some expansion and contraction. If not done right, you can get some leakage, and that will deteriorate your VOC destruction over time. So you want to definitely pick a good system, has good expansion and good leakage control and good welding on that. A catalytic oxidizer typically will use a catalyst bed, and that's going to be about 550 degrees Fahrenheit to 800 degrees. And those are sensitive to silicones, heavy metals, sulfur compounds. If you have those in a stream, probably not a good application. So know your application, know what's in there with your solvent inventories and so forth. Typical applications, and probably most of you are familiar that have some experience, everything from semiconductor, wafer fab, to paint, spray, and finishing, coating of everything from cars, automotive components, wood finishing, could be wood furniture, bowling pins, we've seen applications there, coating of bowling pins, and just about everything that's used on a solvent coating. The food industry, we see a lot of everything from fat fryers to rendering facilities. Fiberglass and carbon fiber, as a lot of automotive components, and just everything is switching from steel and aluminum over to carbon fiber and fiberglass. It gives you added strength, added flexibility, but you also have styrene and other types of VOCs in those processes that need to be abated. Refining and petrochemical and pharmaceutical, that's always been a strong industry. And then everything from soil remediation of small units, bakery ovens, and even metal and automotive recycling has applied oxidizers for those types of applications for VOC control. Again, a lot of the process applications, and it's a wider range. When I first started, I never thought we would see, for metal shredding, we would never see oxidizers applied to that. So the tried and true ones are obviously, web converting, chemical processing, wood products and veneer dryers, resins, MDF plywood plants, pharmaceutical reactors and spray dryers. And then we're seeing a lot of streams these days that certainly have acid gases and halogens that have to be addressed as well with alloy design, and Brendan will be talking about that a little bit. And we can have scrubber options there. So there's quite a bit with all these various processes. I think we're at a poll question here, Mary, so I'll take it over, let you take over here.
Thank you, Brian. Thanks for that great overview. Hey, we're up to our next poll question. Again, don't forget, you'll be able to put your answer in the next slide. So what type of thermal oxidizer are you most familiar with? And you can choose as many as you want. So DFTO, recuperative thermal, RTO, RCO, lots of initials here, right, and acronyms. DFCO for direct fired, catalytic oxidizer, or something else. So let's put you to the next slide. And remember, you can choose as many as you want. And since this is a little bit longer question, we'll give you a couple more seconds to fill everything out. All right, just let everyone finish up and we will take a look at these results and see what everyone's familiar with. I guess not surprising here that the RTO is the one that most people have definitely seen out there, but it seems like we've had a good mix here in terms of other oxidizers that are out there. So nice mix out there in terms of what people are familiar with. And we're going to now pass this on over to Brendan, who's going to talk a little bit more about different components in that.
Absolutely. Thank you, Mary and Brian. Yeah, the poll results make sense, I would say. Not surprising that the regenerative oxidizer is the most common, but I'm glad to see that we have a diverse group, familiarity all around, it seems. So, yeah, before I get into more of the technical aspects, thank you for joining again. I just want to sort of brush over reiterate rather, the working concept behind any thermal oxidizer. And it's really that you have a given flow rate of gas, right? It has particular characteristics. It has a humidity, it may have particulate matter, it certainly has VOCs and HAPs, speciation. But at the end of the day, it's a given volume of gas, and it needs to be heated to a certain time, a certain temperature for a certain amount of time, around a second. So really, you have a flow rate, and it needs heat input to reach a certain temperature. And the way that the oxidizers primarily differ is in the way that they manage the energy input, and that primarily affects, the energy efficiency, the fuel efficiency, and at the end of the day, the operational cost of the unit. So again, while there are many different types of oxidizers, as Brian has alluded to, we'll get into these in more detail. Just want to reiterate that the purpose, the fundamental operating method of all the different configurations is ultimately the same. That is to oxidize VOCs by the means of the 3 T's, time, temperature, and turbulence. So there are certain components, therefore, that are going to be incorporated into any thermal oxidizer system, essentially, no matter the design. We have a process fan to move the gaseous VOCs through the oxidizer. This could be at the front end, called forced draft fan, or the tail end, induced draft, typical industrial ventilation stuff. There's an oxidizer casing, generally, it could be a mild steel or a stainless steel or any number of alloys. This serves as the combustion chamber, or the basis of the combustion chamber. Then you have a burner or some other heat source. Oftentimes it's usually natural gas or a propane burner. It could be an electric heater element as well, anywhere where you can provide heat to the system. Then you have internal insulation to the shell. Most common steels, they don't like to sit over 1600 degrees F continuously. Additionally, that would definitely pose a risk, and I don't think OSHA would approve, certainly. So generally, the outer skin temperature needs to be managed below about 140 degrees Fahrenheit. So you have, it's all insulated internally. You have instrumentation and control hardware to maintain the temperature and flow through the oxidizer. Additionally, to shut down the unit if you lose fuel pressure, compressed air pressure, if you lose the process, anything. And then finally, you have some sort of an outlet, an exhaust stack, where you can measure the VOCs. Otherwise, you may be feeding into another, process equipment like a tower scrubber for post-treatment of acid gases, for example. But anyway, nowadays, the RTO, regenerative thermal oxidizer, is probably the most common of all, which also has heat recovery beds to minimize fuel usage. That's a really important part of the way that it operates. So that's That's the most common that you'll see. So just before getting into the different oxidizers in more detail, I want to direct your attention to this graph. So this shows energy usage in million BTUs per hour. It's a common unit used for 4 different oxidizers, but they're all 10,000 SCFM, and we're assuming 0 VOCs. And it's important, again, to note VOCs are simply VOCs versus your fuel source. The VOCs are a fuel source. So whatever heat you don't add to the system in VOCs, you have to make up with your fuel. If you have a lot of VOCs, you don't need to add as much fuel, because essentially you're just maintaining a flow rate, a system at a certain temperature. So you can see the difference in fuel efficiency is really vast. This is directly a result of the heat recovery capabilities of each of the oxidizers. So the RTO on the far right is the best. But this also, it plays into the applicability for a given process. So oxidizers that require a large amount of heat to stay up to temperature, that would be a DFTO or like a recoup on the left, because they release a lot of heat, so they require a lot of heat input. They can also accommodate very high VOC concentrations. You remember that a VOC is a fuel source in itself. It releases heat upon oxidation. You find that the RTO, where it excels, in very low fuel consumption when running on process around fresh air even, it's somewhat limited to processes that don't exceed 4 to 6% LEL if you don't provide provisioning for that. So if you say, the oxidizer requires less than 1 million BTUs an hour, in this case, to hold its temperature, or your VOC spike to 1.5 million, over time, continuously, the oxidizer will overheat. Now, there's things you do. You include a hot gas bypass to remove heat from the system. You actually derate the RTO. And this is ultimately why the RTO is the most popular and flexible design. Anyway, we'll get into that. I just wanted to make the link that you kind of have fuel efficiency, and that goes hand in hand. It's inversely proportional to the capacity to process high VOC concentrations, all else being equal. Anyway, hopefully this will make sense as we move along. So moving into the different types, we start with the most basic, kind of work our way up. So the way I want you to think about this, that there's kind of 2 general configurations for oxidizers. You have a straight through design, which is kind of a steady state, straight through, and then you have a regenerative design, which is kind of to the side. It's kind of its own thing. The first few we look at will be straight through design, which means you have air moving in one direction, unmanipulated by any sort of flow control mechanisms other than the fan that's pushing it. So here, this is called the DFTO, the direct fired thermal oxidizer. Pretty much is what it sounds like. You have a metallic, usually metallic internally insulated chamber with a burner plumbed into it. This holds the combustion chamber at a constant temperature, around 1600 degrees Fahrenheit, let's say. Then have a process fan driving VOC-laden air through the unit, and it exhausts through the stack. So this is the simpler oxidizer. It also uses the most amount of energy, because you're simply heating up a particular flow rate of gas to a temperature, and then you're exhausting it into the atmosphere without recovering any of that energy, that heat. So it's typically used on lower flow, that would be lower operational costs, lower flow applications where the process is run in batches. It's easy to, shut it down and start it up. Basically just a burner, and the box heats up really quickly. It's good for high LEL processes, up to about 50% LEL. If you control for it, you can do up to 50%, because it requires so much heat for the combustion chamber to stay at temperature again, because you're releasing all that heat. So generally, all these straight through sort of type of oxidizers we're talking about can achieve over 99% VOC destruction if they're designed with adequate retention time. That's always kind of a lever, to play with. Moving forward, a little more complicated, the recuperative thermal oxidizer. This is essentially a souped up DFTO. It has all the same components, only now you have a bit of heat recovery in the form of a single or multi-pass. It's usually shell and tube heat exchanger. So what this does is preheat the process air using the hot combustion chamber air, recovering anywhere from 30 up to 80% of the total heat of the system in a really efficient system. In this case of this image, the 4 parallel arrows here, it kind of indicate the flow path through the 4-pass heat exchanger. You can see it goes back and forth. This substantially reduces the fuel usage, as if you recall from that graph earlier, but it is, significantly more expensive than the DFTO because you have the tubes, the tube sheets, the costly internal high temperature expansion joints, make sure everything's happy at high temperature, as well as, an ambient temperature when it cools down. So this is really kind of the evolution of the DFTO. It's definitely been hugely popular in the past, but for the most part, kind of been replaced by the RTO, the regenerative type, just generally speaking. Moving on to another variation, we have a catalytic oxidizer. This is kind of just to showcase the catalyst portion. This is a catalytic recuperative oxidizer, so again, it has that 4-pass heat exchanger. But here we have a precious metal catalyst bed, kind of resides in the combustion chamber. It's circled in red there. This allows for a bit lower oxidation temperature, around 550 to 800 degrees, as Brian said, rather than like 15 or 1600 degrees. But it does require custom tailoring for the process. It doesn't work for certain things, halogenated, sulfonated heavy metals, things like that. So you need to make sure it's, compatible, essentially. But, what you get for operating at a lower combustion temperature is that you don't have to input as much heat. It's more fuel efficient rather than operating at, heating 5,000 CFM to 1,500 degrees. You have to heat it to 700. So finally, I'm going to move on to the bread and butter, the regenerative thermal oxidizer, the RTO you know and or love, or at least hopefully heard about. Generally speaking, it's the most popular. It can be the most flexible type of oxidizer available today. There's many different types of designs of an RTO, but this design has heat recovery like the recuperative oxidizer, but it operates a bit differently from those straight-through designs in that this recovers heat on a cyclical basis, and therefore it is a lot more thermally efficient. They can achieve up to 97% thermal efficiency generally, and they come in a wide variety of 1, 2, 3, up to 12, plus you could have as many as you want, essentially beds, and can be designed to accommodate very high LEL, 30%, think 30% LEL. If you know what LEL means, I don't know if we explained that earlier, lower explosive limit. It's essentially a indicator of the concentration of the VOCs that you have in your stream. So 100% LEL would mean that you're at the leanest point at which when an explosion would automatically, auto-ignition would occur. So typically you need to stay below 50% for any thermal oxidizer. And there's many options for these that we'll go into as well. But first I want to talk a little more about just how the RTO works. So this is a typical 2-bed RTO, kind of the easiest to explain, and then the rest are all variations of this. So on the right here, so the 2-bed RTO recovers heat via 2 ceramic media beds. Process air is brought in below one of the media beds, which preheats the air before entering the combustion chamber. That's number 5 here. Then it goes down into the second bed, which then recovers heat from the air. So again, the process is preheated, goes through combustion chamber at about 1,600 degrees for a fraction of a second, around a second. Then it exits through the second bed, which removes heat from the process. So for a given cycle for the RTO, the inlet side media bed starts off very hot and is cooled down by the incoming process air. At the same time, the outlet media bed starts out cool and is heated by the air that just came through the combustion chamber. So the temps for the beds kind of act like a teeter-totter seesaw, depending on where you come from, where one bed cools, the other is heated. Once the beds are at their respective kind of temperature extremes, a few hundred degrees apart, your flow control device, whatever that is, in the case of this image, it's the number is 2 here. It's a poppet valve mechanism. The flow control device will switch and reverse flow through the whole system, and the process starts all over again. And then your outlet bed becomes your inlet bed, which is hot, and then your process absorbs heat from that. So this results in really extremely high thermal recovery, really. It does require a split second of flow reversing, which in the case of this two bed allows VOCs to actually bypass the combustion chamber for that split second, escape straight through the stack. So if you see one, you have their process fan, and then for a split second while these two valves at points 2 are switching, the process essentially goes from that bottom duct up to the top duct and out the stack for about a half second. This is why, in part, the RTO is typically rated at a minimum to 98% destruction efficiency, but there are things you can do to capture or mitigate that puff entirely so that it's over 99% effective like the other straight-through designs. But anyway, I want to reiterate, say you have ambient air coming into this thing, generally coming out for a 95% efficient thermal oxidizer, the exhaust temperature will only be 30 to 50 degrees higher than the inlet temperature. So you may have 70 degrees going in and 120 degrees coming out. So that just kind of shows you how thermally efficient these are when you have the combustion chamber in the middle of all of it at 1500 degrees. You're really recovering a large portion of that. And that's why, that's why they're the norm, and that's why yeah, they're great. So, excuse me, which slide is next? Yeah, so the different oxidizer, RTO types, I should say, for the regenerative oxidizer. We have the two bed on the right. It's generally a little bit more cost effective. It's for lower flow rates, generally speaking, compared to the larger. They tend to be larger multi-chamber RTOs. The two chamber is kind of limited to what you can ship easily. So generally 80, 90,000 SCFM. And it's generally standard rated at 98% destruction. In terms of the multi-tower, if it's an odd number design, the 3, 5, 7, etc., that works similarly, except for there's an additional media bed, which is constantly in purge. So essentially, you don't have that VOC puff. Every time you have the bed being purged, all the VOCs are being taken out of that purge bed at a low rate, and then that bed moves to outlet at the beginning of every cycle, so that there is no VOC puff. It will just go. All VOCs would be oxidized before exiting the unit. So, anywho, it's a little more, tends to be more expensive, tends to be higher flow rate. But you can definitely do a smaller multi-chamber RTO as well. Additionally, you have the rotary valve RTOs. Typically, there's many different configurations, but it could be a kind of a cylinder that, from a plan view, it kind of looks like a pizza pie with triangles cutting it, and you have inlet, outlet, and purge sections, very similar to any other 3-chamber, but the whole system kind of rotates on an axis. So in the interest of time, keep moving forward here. So again, just reviewing factors that influence destruction efficiency, we have the 3 T's: retention time, temperature, and turbulence. But additionally, I added here the VOC puff, particularly for the 2-chamber. Quick retention time calc is just, it's the volume in the combustion chamber divided by the actual flow rate through the combustion chamber at that high temperature. Yeah, so now talking a little bit more about that VOC puff. I think I mentioned the puff capture module for a 2-chamber effectively makes a 2-chamber act similarly to a 3-chamber or 5-chamber with a purge bed, but it doesn't. You don't need an entire new bed for the RTO. So it's this additional enclosure, and I think we have a little. There we go. That red circle. That additional box in the back of the additional poppet valve. It captures that 1 second of VOC puff. Generally, it's sized to capture a few seconds to ensure 100% capture efficiency. But it then reroutes that VOC puff back to the inlet of the unit during that cycle where it's oxidized. So here we have an example. Hopefully this kind of helps for those who like seeing graphs. So we have the difference between a 2-chamber, standard 2-chamber on the left, and a 3-chamber, or you could say a 2-chamber with a puff box on the right. So the yellow line indicates VOC inlet in concentration, and the blue line indicates the outlet. So for the most of the time, you could think of destruction efficiency as 1 minus the area under the blue curve divided by the area under the yellow curve. Those spikes you see in the blue are the VOC puffs. So every 4 minutes, give or take, depending on how you set it up, you have a VOC spike. In the case of the 3-chamber or the 2-chamber with puff capture box, you eliminate that spike and you oxidize close to 100%. And so that's where you can get those really high destruction efficiencies if it's required. Additionally, really important, really cool feature, it's kind of a simple solution, but it works really well. I was explaining how the RTO requires very little heat to stay at temperature, right? But in the case, if you have a lot of process VOCs, or if you have a very variable process where you have maybe a little VOCs at a time, but you have a lot, you have some spikes, but you have to operate the oxidizer all the time, you would want to install hot gas bypass. It essentially derates the thermal recovery of the unit. There's a refractory line damper in the combustion chamber somewhere. It routes to the exhaust stack or the exhaust manifold, and it pulls hot air out of the unit. So this allows you to operate at very high LELs with the RTO. And anytime you're operating in this zone, the RTO has enough heat to get by. What you're saying is that, I need to expel some. And you can essentially modulate this damper to maintain that 1600 degrees in the combustion chamber. And you don't have to use any natural gas or propane at all. So it's a great way to be if you can make your process work for you like that. All you got to do is push air through it with your fan. Additionally, we talked a little about flow control. That's a really crucial part of the multi-chamber or the regenerative thermal oxidizer. So there's different ways to do it. You have the poppet valve or a standard butterfly valve. You can see on the bottom right is a large unit with butterfly valves. Exhaust manifold on the right, inlet on the left side on the bottom there. But these can all be, pneumatic, hydraulic, electrical. I mean, pretty much you name it. Additionally, the rotary valve, same thing. It generally requires a purge air fan to kind of block and bleed in a way that the seal all around the entire valve. So, but it works. You have air coming in through the bottom generally. It goes up into the combustion chamber and then down again. So it works like any other thermal oxidizer, or RTO, I should say. Once again, just to review the options, I kind of talked about a few, but the puff capture module or the third tower RTO, these are great for, odor problems. If you need to, sometimes a couple ppm is enough to set off the human nose. So that's always an option. Catalyst options, you can incorporate a catalyst into an RTO as well as a recuperative unit or a direct fired unit. Again, it just essentially lowers the temperature which that you need in order for full oxidation. Instrumentation, there's all sorts of options with data collection and with Class 1 Division 2, explosion-proof equipment. Metallurgies for acid gas applications, stainless steel, RE2205 duplex, a whole host of options. Low NOx burners is very popular. It really depends on what state you're in, let's say. But lately it seems, most oxidizers are requiring them. And then finally, we do have secondary energy recovery for the RTO, because the RTO is so energy efficient. A lot of times there's just not much you can get out of the exhaust of an RTO because it's kind of been cooled down by the internal system of it. But on other thermal oxidizers, it's definitely been used a lot. So I'm going to hand it back over to Brian just for a second here to talk about secondary heat recovery options.
Thanks, Brendan. Great job. Obviously, any oxidizer, especially like the DFTO, when you have a very high stack temperature, if you're coming in at ambient and going out at 1500 degrees on a DFTO, you have a lot of BTUs going up the stack. I know particularly in Europe and even in Asia, energy costs are a lot higher than here in the States, but most customers today do look at secondary energy recovery. It could be as simple as an air-to-liquid heat exchanger like a hot oil or glycol, or even air-to-water in the stack, a little coil. Chiller condensers we see out west in arid climates. That makes sense for both AC, air conditioning, as well as chilled water. You'll see that a lot in the printing industry. The picture on the left, the very top of the unit just below the stack, that big box, that's a chiller condenser system, a secondary system that was put on that RTO. And that customer had a lot of need for both AC and chilled water in the plant in the process. Some customers may think that they will need a future secondary heat exchanger. We can design a provision in there. I think most RTOs can be designed for that, to have a spool piece or whatever. And also, if you need to bypass the secondary heat exchanger, a lot of times you may not need all that heat for in-plant heating on air-to-air in the winter, so you can bypass that. So you need to think of all those things to design into your secondary heat recovery section and module. Here in the States, and I know in Europe, there are potential utility energy rebates for being very cost efficient and energy efficient. And you always want to consider what your current energy costs are, because they're only probably going to go up from here. So if you're going to have this RTO around or an oxidizer or a DFTO for 10, 20, 30 years, think of your future energy costs and try to minimize those. That's very, very important. So I guess, Mary, we got the poll question here for you here.
Yeah. We're at our last poll question here. Thank you, Brendan and Brian. And hopefully you guys are not confused, but if you are, just remember you can shoot us a question, and even if we don't get to it during this presentation, we will definitely get back out to you and make sure that it's answered. So what type of thermal oxidizer, if any, do you have installed at your facility? And there's a couple options there: DFTO, catalytic oxidizer, two-bed RTO, multi-tower RTO, and as some of you may have seen, I only have a VOC destroyer license plate. That's probably what I have. I think that's my answer, but here you go. Please place your answer here, and we'll take a look at the results. We'll give everybody a couple seconds here.
There are no wrong answers, right, Mary?
Correct. It's one of those easy questions for the day. No wrong answers. That's right. All right, let's see what we've got in terms of our results. Okay, so we are looking at a majority here have a two-bed RTO. Hey, look at all those people who have the VOC destroyer license plate. That's awesome. So and then we also have just a catalytic oxidizer, and the DFTO are almost in the same percentage area. So not too many out there that have 3 or more towers. I think this one passes back on to Brendan.
Right. Absolutely, thank you for that. So to kind of review here, before we get into some examples, thermal oxidizer dues, we decided we're gonna be optimistic here and just focus on what you should do. So size the oxidizer for maximum and minimum flow, bracketing process data. This is really important. One of the the worst things you could do is to just undersize the unit. It's a major capital expenditure, and essentially there's not a lot you can do other than you redesigning the whole thing or putting in an additional oxidizer. It's important to accommodate or think about what the minimum and absolute maximum flow rate you're going to see. Again, the same goes for temperatures and VOC loadings. You don't want to install an oxidizer and then find that it's kind of starting to overheat, depending on how you run your process. Different times when there's plenty of options to be able to accommodate high VOC loadings. Again, you need to consider your metallurgies. It's always important. Sometimes, if you have some sort of a sulfonated compound, it may not be very reactive in itself. The oxidizer kind of likes to create, it likes to break things down, and it also, the byproduct of thermal oxidation is water and it's CO2, right? So a lot of those halogens like to react with water and create acid gases. So certainly need to consider that, and that's something that, a thermal oxidizer provider should be able to look at and tell you what metallurgy to go to. Again, future expansion, this kind of goes with number one, but you definitely want to be thinking long-term. Locating the oxidizer close to process also can be surprisingly important if possible, or you may need to you need to manage at least the temperature of the duct. So you have a process going on at 100 degrees, but you have a long line of duct going to the oxidizer, and that gives the opportunity to cool down the process a bit and condense some of those compounds. It can pose an issue for the process fan for the oxidizer as well. But again, yeah, energy costs and plant expansion. I think what Brian and myself are trying to stress is that these things, good ones, they'll last 20 years or more. So you really want to consider what's the best option in the long term, in terms of if you're going to need a slightly larger one a couple of years from now. Additionally, how much money are you going to save by getting a little bit of additional heat recovery right now? It can really add up substantially. Yeah, there's a lot to consider, but generally, if you stick to these do's, you don't even have to worry about the don'ts. And moving forward, I guess we have a number of installations here the last few minutes. Brian and I will kind of run through these.
Yeah, we have quite a few here, and to the sake of time, we'll probably go through some of these fairly quickly, but I know, like Mary said, this will be on the website here, the SECO certified website, so you can always come back and look at these. We'll have a bunch for RTOs, including multi-tower units, 2, 3, 7 chamber. There's in the upper right, there's a 3-tower as well as a 5-tower out of stainless, and then there's 2 small 2-chamber units in the upper left. So we'll try to get through these very quickly, and then show you some examples of the DFTOs, the direct fired, and the recuperative units. Recuperative uses, of course, the shell and tubes, typically heat exchangers in the lower left. There's a DFTO in the middle on the lower part. There's almost a flare stack DFTO, a vertical one with tangential burner firing in the upper left. Recuperative is in the upper right, and that has secondary heat recovery on it. And oxidizers, even if you have small point sources, they can be mounted on trailers. We and a lot of other people have done smaller units for soil remediation, as you can see on the trailers. Between 500 and 2,000 CFM, you can mount typically on trailers on the lower right. I'll give you some quick examples. Here's 3 units here, 3 2-chamber units in Korea at a chemical intermediates plant. Typically, what they're doing there is acrylonitrile and polymers. It is a forced draft system. There's redundant fans on each of the 3 RTOs. 2 of the RTOs share a common stack. The customer wanted this designed in, but you can see there's the collection system with the duct. 95% heat recovery, and these had turbulent flow saddle media. Another example, here's 2 3-tower units sharing a common stack with induced draft fans. This is on a spray coating and metal coating type application, and there's also a concentrator system in the back of this. It's typically alcohols and toluene that they're seeing on this type of application. But again, they went with induced draft fans on this application, and the 3-chamber RTOs are each 65,000 SCFM. So they have that dedicated purge chamber that can alternate. It has structured block media. These 2 are great examples of point source RTOs installed. This is actually installed on the roof of a client over in Taiwan at a wafer fab facility in semiconductor. They put the larger unit in first and then built the stack to handle a second one when they added additional wafer fab clean rooms. Those have 97% heat recovery, 99%, I think 98 to 99% VOC DRE. But very low profile, very good for a rooftop mount. Most of our applications and most of what you're going to see is typically ground mount outside, sometimes on a mezzanine, Sometimes in a courtyard, as this case, this is a 5-tower, 83,000 CFM unit. It was in a courtyard of a rubber processing plant. Very tight application. They still had to have access for fire, access for maintenance. So this is a long rectangular type top plan view here. This system with the extra purge has provided 99.3% consistent DRE since 2003. Also, I think as Brendan mentioned earlier, you may need pre-filters on some applications. There's carbon dust in this application, tough application in rubber processing. So know if your application does have dust, RTOs will make great filters. They really do, but you don't want to change that filter media, which is the ceramic media. It can be expensive and time consuming. So if you do need point source filters upstream, certainly do that. Here's a typical low profile unit, again outside ground mount. This is on a web coating type application, high solvent hot gas bypass, because they can occasionally get up to 20% LEL. And again, just low profile, so you want everything that's accessible pretty much from the grade. Here we'll try to wake you up a little bit with Halloween. This is not a haunted RTO. This is just we had some special effects with a nighttime shot of a roof-mounted unit at a Flexo printing and packaging plant. And again, this has multiple processes going into one central RTO. So they had individual fans pushing up from each process. And this RTO does have an AC drive like most of our units have, and what you'll see, I think, with any RTO. So it automatically will throttle back if you're only running one press or if you're running all 8 presses into the unit. 99% destruction, low profile, which works out well for a rooftop application. This is a typical rotary valve or indexing valve type RTO, cylindrical type design with the media. The burner is on top in the dome. This is a system that one of our Seco China Saudi group had put in China. The indexing valve is on the lower portion, and you can see that there's an access to it. There's a separate purge fan on that to keep positive pressure on the seals. The valves, there's basically no valve. It's just that indexing valve at the bottom or indexing device. There's 12 heat recovery sectors. If you looked at a top plan view, so it looks like cutting a piece of pie or a piece of round pizza into 12 shapes. So that gets 99% destruction and 95% heat recovery. This is a low profile unit, typically even on larger sizes is 70,000 CFM. It's on a particulate stream, so there's reverse air dust collectors ahead of it. It's on a foundry casting line, so you will get some sand dust that does carry through. So formaldehydes, benzene, alcohols, that's typically what this application is seeing. Brendan, I'll let this over to you now with the concentrator here.
You know what, guys, I think in the interest of time here, I think that we probably are going to need to get ourselves to a couple questions here. But just for everyone, there are some additional examples here. The PDF of the slides is available over to the right in that resources area, so you can definitely take a look through the rest of the examples there. And if you have any questions, again, shoot them off to us and we will definitely get back to you on them. And I do want to thank Brendan and Brian for joining us today and doing this presentation, and thank all of you for joining us. We know your time is valuable. Let's try and do 2 questions here real fast. And just a reminder to everybody, you need to be here for at least 50 minutes of the presentation, and you need to complete the quiz that's over on the right-hand side. Let me show you the widget here. So down here, take a look at those last 2 widgets. The second to last is where you test. The last one is where you make sure that you've completed everything. So if you need that PDH portion, that's where you need to go. So let's pick up just a couple questions here real fast. And there's one here that I thought was kind of interesting as we are heading into the winter time for a good portion of our U.S.-based customers and attendees. Do RTOs need to be winterized?
Yes, they do. Obviously, if you have compressed air for the flame scanners, and I think every type of thermal oxidizer uses a flame scanner, Mary, you want clean, dry, compressed air. Poppet valve options on oxidizers, Brendan and I showed a lot of examples today on those. those have to have clean, dry, compressed air as well. So you may need a newer desiccant dryer. You may need to do some heat tracing of lines, especially if you're in the North Country or you're in Upper Canada or in the polar regions or Scandinavia. Also, I would definitely not locate an RTO.
Absolutely. You can even get minus 40 or even minus 60 degrees F rated, gas train equipment, because you don't want those gas cells conking out.
And they can do that. And the other thing is locate your RTO. When you do locate it, make sure it's not under an overhang that was typically built up with ice and icicles come tumbling down and hitting the top of the RTO or the piping train or the burner piping. So there's a lot of things that have to go into that, Murray. But yeah, definitely they need to be winterized.
Great. All right, one more question here before we go quiet. And just a reminder, we will go quiet here after this question, but the actual platform will be up for another 30 minutes so you can finish up everything that you need. So let's take a look at one last question here. Does my thermal oxidizer fan need an AC variable frequency drive, and when do I need it?
I would say that yes, generally speaking, and virtually most thermal oxidizers will have an AC drive on it, even if it's to bring it up from a cold start, and you'd operate at, say, a third flow or quarter flow capability. Most of the RTOs that Brendan and I showed you today have multiple processes going into a larger RTO, and for that, if you have one process down and still have one up, the AC drive will automatically throttle it back. I think, Brendan, there's also some energy rebates sometimes, too, on the AC drives as well.
All right.
There
Awesome.
can be, yes. Sorry, I got bumped off. That was a technical difficulty.
Well, that must be our sign that we need to finish here. So.
I guess that is.
So thank you, Brendan and Brian, and thank you everyone for attending here today. We hope you will join us for our next event on November 18th on industrial ventilation design. You can go to secocertified.com or down to the little check mark widget on the bottom and sign up for that. Otherwise, we are going to go quiet, but the platform will stay live here for about another 20-25 minutes so you can finish everything up. If you ask a question, we will definitely get back to you with an answer either here live while you're still attending or in an email later on. Thank you again so much for coming, and we hope you have a wonderful day. Take care.